Let's see this question. Construct a minimal finite automata that accepts strings over 0, 1, 2 whose integer equivalent is congruent to 3 mod 5. This is similar to previous questions when we will solve it using the shortcut we discussed in the previous video, right? So given alphabet is 0, 1, 2. This means the strings are ternary. The strings are in ternary number system, and each string is made up of 0, 1 or 2, and its integer equivalent is congruent to 3 mod 5, right? It means when we divide the integer equivalent of w with 5, it should leave a remainder 3, right? So since we are dividing with 5, what are all the possible reminders when we divide a number with 5? They are 0, 1, 2, 3, 4, right? These are the 5 possible reminders when we divide a number with 5, and we are concerned only about the remainder 3, right? Since we have 5 reminders, we will have 5 states. They are q0, q1, q2, q3, q4. So all the strings which we have in our language are divided or classified into 5 classes. Q0 represents all the strings whose integer equivalent leaves a remainder 0 when divided by 5. Q1 represents all the strings whose integer equivalent leaves a remainder 1 when divided by 5. Similarly for 2 and 3 and 4, right? So we have 5 states. Now 5 states and 3 input symbols, right? So the state transition table will look like this. We will have 0, 1, 2. All these are the input alphabets, and the states will be in the rows q0, q1, q2, q3 and q4, right? q0 is always our initial state. Since we are concerned only about the remainder 3, we will make q3 as final state, right? So how do you fill this state transition table? We start with q0 at the leftmost column and continue to towards right in this way, writing the next state. So here I will have q1 and here I will have q2, and you write all the states sequentially until you reach the last column, right? This is the last column, so you stop it here and then continue with the next state q3, q4, right? You are done with the states. Q4 is the last state, right? And then you start again with q0 from the next column until you reach the last column. Now q0 is the next state, q1, q2, q3, q4, and then q0, q1, q2, q3, q4. This is the state transition table for minimal finite automata that accepts strings over the ternary. This is ternary number system whose integer equivalent is congruent to 3 mod 5, right? This shortcut works for almost all the problems of this kind, but you need to be very careful when you are working on problems like this. Like when you are asked to find DFA that accepts all strings over all binary strings whose integer equivalent is divisible by n, right? That means if a integer equivalent is divisible by n means it is leaving a remainder 0, right? So in this case you need to be very careful, because with this shortcut you can say that since we are dividing with n, there are n states q0 through qn, and we are concerned only with remainder 0, you will make q0 as our final state, right? If you make q0 as our final state, that means you will be accepting epsilon, right, which is not in our language. So you need to add one more state, let's say qs, and make this as initial state, and the transitions from qs will be q's on seeing 0 it will go to q0, and on seeing 1 it will go to wherever q0 is going to on 1, right? Let's say q0 is going to q1 on seeing 1, so qs will also go to 1 q1 on seeing 1, right? You will add one more state like this and try to minimize the DFA after constructing the DFA from this shortcut, right? Let's take an example. Let's say you were asked to find the DFA for strings accepting, for binary strings whose integer equivalent is divisible by 3. So your string integer equivalent of the string is divisible by 3, right? So this is how you will be writing, right? So here we have q3 states, q3, q0, q1, q2, because we have three reminders 0, 1, 2, and q0 will be our final state because we are concerned only about the remainder 0, right? So ideally, if we go with the shortcut, you will have, and this the input alphabet, let's say it is 0, 1. This is binary string, so your input alphabet is 0 and 1. The states are q0, q1, q2. Initial state is this and final state is also this. And how do you fill it? q0, q1, q2, q0, q1, q2, right? This is how you fill the state transition table, right, using this shortcut. Now the now we draw the DFA out of this state transition table. Let's say this is our initial and final states, q1, q2, right? We have these three states. On seeing 0, I will go to q0. On seeing 1, I go to q1. On seeing 0 from q1, I go to q2. On seeing 1 from q0, on seeing 1 from q1, I'll go to q0, right? On seeing 0 from q2, I'll go to q1. On seeing 1 at q2, I'll be in q2 itself. So this is our DFA based on the state transition table. But this DFA accepts epsilon, but the language has only strings like 0, 1, 1, 1, 1, 0, and 1, 0, 0, 1, and so on, right? All these strings are divisible by the integer equivalent of all these strings are divisible by 3, right? So there is no epsilon in this language, but here we have initial state as final state, but so this is wrong, right? So we add a new state qs, which is our new start state, and we remove this as initial state. q0 is not our initial state anymore. Qs is our initial state. So on seeing 0 from qs, we go to q0. On seeing 1 from qs, we go to that state where q0 is going to on seeing 1, right? q0 is going to q1 on seeing 1, so qs is also goes to q1 on seeing 1, right? This will, adding this state qs will eliminate epsilon from our language, and now this is a DFA. This may or may not be minimal DFA. You need to check whether it is minimal or not and you need to construct a minimal finite automata out of this.